If you could shine a flashlight at a black hole, would its light fall straight in or could it circle forever? Here's the twist that sounds like science fiction. There's a thin ring of light around a black hole, often called the photon sphere, where photons can orbit. But orbit here doesn't mean stable. It means precarious, so precarious that a tiny change in a light ray's path can decide whether it plunges into the black hole or escapes to infinity. What looks like a tidy geometric feature becomes a chaotic separator. And once chaos enters the game, predictability fades, except for one special kind of chaos we can still measure: Lyapunov chaos. So the real question is not just, what is the light ring, but why does it behave like a chaos engine, and what does that teach us about the most extreme gravity in the universe? Before we get to the ring, we need the older misconception to let go of. For a long time, people thought black holes were simple sinks. Light falls in, end of story. General relativity does predict capture, yet it also predicts something subtler. Around a non-rotating black hole, there is a radius where the gravitational pull can balance the tendency of light to travel straight. The photon sphere forms a boundary between two outcomes. Below it, every photon is inevitably captured. Above it, photons can potentially escape. But that boundary is not a wall. It's more like a ridge in a landscape. A ball on a ridge can remain for an instant if perfectly placed, yet any nudge makes it roll off, either inward or outward. Astronomers didn't discover this ring by watching individual photons. They inferred it indirectly, through the shadow of a black hole and the way strong gravity bends, delays, and magnifies light. Theoretical physicists had mapped the geodesics, the paths of photons, long before the first images came, but connecting those paths to chaos metrics was the deeper step. Now for the deep dive. Picture a photon as a tiny arrow in space-time, always moving at light speed while gravity changes the direction of its trajectory. The equations that govern these trajectories are deterministic. Given a starting position and direction, the path is fixed. The surprise is that the photon sphere corresponds to an unstable circular orbit. It's a solution, but not an attractor. To see how chaos emerges, imagine releasing many light rays that start extremely close to the perfect photon orbit, so close that, visually, you might expect them to behave similarly. They don't. The slightest difference acts like a mismatch in initial conditions. After some time, those rays diverge exponentially in how far they move away from the unstable orbit. That exponential sensitivity is the hallmark of Lyapunov instability. There's an elegant way to understand it using the ridge analogy. On a ridge, the springiness that would restore you toward the center is missing. Instead, motion away grows under the influence of the geometry. Near the photon sphere, the effective potential for photon motion has a maximum. When a photon hovers near that maximum, its fate depends on whether it rolls down toward the black hole or down toward escape. In a Schwarzschild black hole, the photon sphere sits at a particular radius set by the mass. For rotating black holes, the picture becomes richer. There are different families of photon orbits, some co-rotating, some counter-rotating, and the instability can differ by direction. In both cases, the key mechanism is the same. Unstable circular geodesics create a gravitational lensing structure that acts like a chaos filter. Rays that pass near the ring can loop around multiple times before deciding their outcome. The number of loops increases dramatically as the initial direction is tuned closer to the critical set, yet tuning perfectly is impossible in practice. This is why the light ring isn't just a static glow. It's a dynamic boundary between capture and escape. When researchers numerically integrate photon geodesics, they can compute how nearby trajectories separate. The Lyapunov exponent quantifies the rate of divergence. That exponent becomes a bridge between geometry and chaos. Space-time curvature shapes an instability, and that instability shapes observables such as the fine structure of the black hole shadow and the timing of light echoes. In other words, the ring is a stage where light rehearses eternity, then abruptly forgets it, thanks to exponential sensitivity. So why should this matter beyond elegant math? Because chaos near black holes is a window into how nature converts uncertainty into irreversibility. In many physical systems, chaos limits prediction without violating determinism. Black holes add an extreme gravitational amplifier. The photon sphere turns tiny imperfections, finite angular resolution, thermal motion in an emitting plasma, even quantum fluctuations in principle, into macroscopic differences in what light escapes. That affects how we interpret black hole images. The shadow is not merely an absence, it's a consequence of photon capture probabilities shaped by unstable orbits. It also affects gravitational wave astronomy indirectly. Compact objects that graze strong field regions can excite echoes and modulations linked to similar unstable structures. And on the theoretical side, chaos connects to deep ideas about information thermalization and the nature of quantum chaos. Even if photons are classical in these calculations, their behavior near a horizon motivates questions. How quickly does information become scrambled in a universe ruled by horizons and tidal stretching? There's also a pragmatic implication for future instruments. As we improve angular resolution, we can probe finer features in the ring and the shadow's boundary. Those features encode how quickly trajectories diverge, and thus how sharp or fuzzy the transition between capture and escape becomes for real emission regions with finite size. Lyapunov chaos becomes not just a concept, but a measurable ingredient in translating observed light patterns into space-time parameters like mass and spin. So the journey ends with a simple, unsettling picture. The black hole light ring is a place where photons can momentarily behave as if gravity has made a circular path for them. Yet the path is unstable, like standing on the top of a hill. Because it's unstable, nearby rays separate exponentially, creating Lyapunov chaos. Because of that chaos, the boundary around a black hole isn't a solid surface. It's a probabilistic event shaped by the geometry of unstable orbits. And once you see that, the shadow stops being a silhouette and becomes a diagram of unpredictability written into space-time itself. If you want more science that turns cosmic mysteries into measurable mechanisms, subscribe.